So in this video, we'll be talking about alkenes. And alkenes are simply just carbon chains with double bonds inside of them. And so anytime you see a carbon chain with a double bond inside of it, that's a type of alkene. And so I drew some examples here below. You can see that in this example right here, there's a double bond present right there. It looks like I just drew it into a triple bond, but I'm really just trying to emphasize the double bond. And in this example as well, you can see the double bond is right over here. And the double bond in the third example, you can see the double bond is over here. And so the reason that I drew these three different examples is because I'm trying to illustrate that you don't need, there's no one standard definition for an alkene. It's any carbon chain with a double bond. And so now I'm going to be going through some types of reactions that you could have with alkenes, and I'm going to go through 5 reactions in this video, and I'll have another video following it with the remaining 4 reactions that are important for alkenes. So the first reaction I have here is just an H2 addition. And what an H2 addition is if you have an alkene, as shown by this reagent right here, then what you can do is just simply add H2, and that's just 2 hydrogens attached to each other, and that'll just put the hydrogens in the position where the double bond was, and it'll remove the double bond. And so that's the first reaction you can do. And so if you want to turn an alkene, which is a doubly bonded carbon chain, into an alkane, you can just apply H2 to do that. The next reaction, which we'll talk about, is the addition of Br2. And what that does is it uses the double bond of your alkene, and it actually just puts 2 bromines on either end of the double bond, as shown here. So here you can see is the product, and you can see that there's a bromine addition here, and there's a bromine addition here, and it replaced where the double bond was. And so now what's important to keep in mind about this is that it actually adds in the anti-addition, as shown down here. Anti just means that they're not in the same plane. They add in different planes from one another. I would also say that this reaction can be done with not just bromine, it can be done with any diatomic halogen. And so what I mean by that is you can do the reaction with Cl2, you can do the reaction with I2, you can do the reaction with a number of different dihalogens. But this is mostly important for just dihalogens in general. The next reaction is the addition of HBr, and this adds very similarly to the dihalogen scenario as Br2 did. All it does is it takes where the double bond was, and it just replaces it with an H and your halogen. So now what's important to keep in mind about this type of reaction, though, is that, well, what if you have a scenario where there's where the 2 ends of the double bonds differ from one another, as in the second scenario down here. And what you do for this one is the bromine, or the halogen in this scenario, gets placed towards the carbon that's surrounded by more carbons. And so what I mean by that is if we look at our double bond here, we can see that the 2 carbons that are involved in the double bond, which is this carbon and this carbon, well, one of them, this carbon over here, is only connected to this carbon. Sorry, not drawing out. This carbon right there. Okay, and so that's just one carbon. But the carbon that I just underlined, this one, is connected, or is touching this carbon here and this carbon here, and that's 2 of them. And so that's considered the more tertiated carbon, and the bromine or the halogen in the scenario will add to this one. And so I showed that down here. Okay, and that's going to be a common motif that you're going to see throughout organic chemistry, that something will always add in what we'll call the more tertiated position. And when we call it the more tertiated, all we mean is the position that's surrounded by more carbons. So the next reaction we'll talk about is the addition of Br2 and H2O, and that's when you add them together. And this is very similar to the HBr reaction and the Br2 reaction, that you're going to have a bromine take one end of the double bond, and instead of a hydrogen this time, you're going to have actually an OH, so an oxygen and a hydrogen, which we call an alcohol, take the other end. And what's important to keep in mind about this one in regards to the stereochemistry of it is that the OH, or the alcohol, is going to add to the more tertiated position in a scenario where there is a more tertiated carbon. And we explained how you find tertiated in the last example. The final thing we're going to be talking about, the final reaction, is going to be H2O in the presence of H2SO4. And what that's going to do is that's just going to add an alcohol to the more tertiated position and a hydrogen to the less tertiated position. So once again, I illustrated the more tertiated and the less tertiated. In this scenario down here, you can see that the alcohol added to the more tertiated position while the hydrogen added to the less tertiated position. And we call typically the less tertiated position the Markovnikov position. This reaction also occurs in the syn addition, as opposed to the anti-addition, which we explained for Br2. Syn just means in the same plane. And so, just to recap, we can see that with a number of these different reactants, with our alkenes, we can do lots of different things. We can turn it into an alkane with our H2 addition. We can turn it to have two Brs attached to it with our Br2 addition. We can make it have a hydrogen and a bromine attached to it with our HBr addition. We can make a bromine and an alcohol attached with our Br2 and H2. And finally, we can add an alcohol and a hydrogen. In the following video, I'm going to be going through the remaining 4 important reactions which are worthwhile for alkenes.